Hello and welcome to day 3 at 17:15. It's kernel hacking exploitation time, so you are to expect a technical talk. Please welcome from Italy, twiz and sgrakkyu.
Hello everybody, thanks for coming. We're going to talk today about kernel exploitation. The talk will roughly be divided in 2 parts. My part will be covering the Solaris ultra SPARC scenario, while sgrakkyu will tell you about Windows exploiting and race condition on the Windows kernels. We will focus on the ultra SPARC architecture. It's a nice architecture from an exploiting point of view because it's a little bit harder than the x86 architecture you're probably more familiar with. It is an implementation of the SPARC v9. It provides support for a fully separated user land and kernel land other space. That means that a pointer in kernel land has no meaning in user land. It also provides execution permission, so you will have pages where you can't execute from. When you have to exploit something, you have to know your enemy. So we have to figure out how the Solaris SPARC architecture lets you implement the separation between user land and kernel land. This is a key thanks to context registers. The MMU provides 2 context registers which are settable. One is known as the primary context register, and the other one is the secondary context register. There is also one more context register, which is hardwired to 0, and is known as the nucleus context. Trap handling and kernel code runs at the nucleus context. Each context register is a 13-bit value, and this value is used by the MMU when you reference a memory address to translate it from a virtual address to a physical address. If you specify a normal instruction and you're in user land, then you will be using the primary context. If you specify a particular instruction, which is an alternate instruction, load or store alternate, and you specify with it another space identifier, then you will be able to use the secondary context register to reference memory. When you are in user land, you usually have a primary context and second context which are equal. When you are in kernel land, the nucleus context is the primary context register, and the process which traps into kernel land, its context register will be the secondary context register. So, checking that, you can see a small stub of code which will copy data from the user land to the kernel land. The nice thing is that if we manage to execute a stub of code like this one, this is awful SPARC assembly. It is just like storing a byte, branching, keeping on copying, and you see the last instruction, which has the A at the end, which means that you can specify an address space identifier and then access the user space. The good thing is that if we can start executing that, then we can copy whatever we want from the user land, from our process, inside kernel land. But we have a problem. How do we start executing that? Or talking in an exploiting way, which is our return address. Of course, we can't store the shellcode in user land, as happens usually on x86 architectures. And we can't use a no-access area. For example, the kernel stack each process has is allocated from the sgrakkyu, which gives you memory. And this memory is marked as non-executable, so you can't store a shellcode in the stack and reference it. And of course, we can't brute force in the kernel, or it's just a boot. So we need to get information from the kernel. And it's good because Solaris gives you a lot of information. That's probably because the Solaris kernel has been a closed source kernel for a lot of time. So they had to give to the developers a wide range of information to handle the kernel. Every running process has associated a property structure. The property structure you see there has an address, the one which is in blue, which is exported to user land. This is a great news. This means that we can know something inside the kernel from inside the user land. We know exactly where something is. So we take a closer look to this structure, and we figure out that inside this structure, there is the user T structure. You see all these members? All these members are somehow controlled by us. Is the name of the program we are executing, is the pointer address of our environment, there are the parameters which are on the command line. So most of the members of this structure are under our control, and we know exactly where they are because the address is exported. So, and there is even a more interesting news. These parameters, these values are stored in a place inside the kernel which is executable. Solaris developer decided that because these parameters are quite less likely to change. And so they thought it was not necessary to put execute permission protection on them. One of them, which is particularly interesting and that we will use during the talk, is the command line. You see, it's basically a char array of 80 bytes. So we have 80 bytes for our instruction. We can put whatever we want in those 80 bytes, and we know where it is. So what we can put? We can put the shellcode. So if we put it on the command line, then we will be able to use it as a return address. We will be able, from inside our exploit, to jump there and start executing. At that point, we have 80 bytes. But we have to check one more thing. You know that on UltraSPARC, each instruction is 4 bytes long. So every time you access an instruction, every time the CPU accesses an instruction, it checks if the address you are accessing is aligned on a 4-byte binary. And if it is not, it will be a trap, it will be a panic. So what we need to check if this offset is actually really on a 4-byte binary. And it is not. But it's not really a big problem. We just skip 3 bytes, and we are on an aligned address. So we have space for 19 instructions. Well, if you're used to x86 shellcoding, you might think that 19 instructions are very few. Well, actually, 19 instructions are more than enough for 90% of shellcode you will be using inside the kernel on Solaris. But anyway, suppose that you need more. Suppose that you need to store a lot of lockings, or there are a lot of problems. There are other things to handle. Well, we can just chain different processes. We can launch 10 processes, gather 10 different addresses, and we will have all the space of every single command line. We just put a branch at the end of our shellcode. Remember the delay slot on Solaris? So remember to put an instruction after your jump, which will be executed actually before transferring the control, and then you're done. You have your shellcode. So, what I was saying, there is a shellcode. This is a working shellcode, which will give you UID 0 on Solaris kernels if you start executing it, given that you don't trash the stack. We start from the bottom. The fact that we don't trash the stack is very important, because return restore expect to find somewhere to return into. And this information is provided by the stack. So if you're not exploiting on the stack, this information will be there, and you will be just using the stack that the caller of your exploiting function has set up for you. This is good, but just remember that that function will never finish, will never get to the end of its code. So if there is any lock pending or anything you need to do in this function, you need to have done on this function, you have to do it by yourself. We skim quickly on the shellcode. It's very simple. We start checking, we need to get somewhere where the credentials are. The normal way to get an exploitation done from the kernel point of view is just to put into 0 the structure which has the information on your credentials. So the first thing we check is that there is a cartridge macros to get the current running processes. What we see is just that on G7, global register 7, there is always stored the address of the thread structure. From there, we need to reach the proxy structure, which is where the credential will be stored. Well, there is one more pointer of indirection we will see in a short. And we just use MDB, this is the kernel version of MDB, to check this offset. You might think that this offset is something like a magic value. Well, Solaris 9, Solaris 8, and Solaris 10, and OpenSolaris all have this value, so you can use it pretty safely. If it will ever change, it's just a matter of you name -A, and you will know on which kernel you are, and you will know the value. Actually, not much people tends to change the state of the Solaris kernel, so you're pretty much safe. The second instruction we do is go into the credential struct, which is the one which will hold all the information about your UID. This is an example from a credential struct which is already 0. Not a great example, sorry, but it's already 0. As you see from there, we store the value on G0, which is 0, which is because G0, global register 0, are coded the value 0, which is very good because we don't have to put it into the shellcode. And we store it from the address of the credential struct +4, so on UID. This is more than enough to execute some code to get an exploit done from inside the Solaris kernel. That's good. But we need to trigger a condition which will make us execute some code. And so one example of an exploit kind of type, an exploit type, which doesn't trash the stack, is the Slab overflow. We will talk now, we will see now in not many details, but quite precisely what Slab overflow is and how to handle it. You know that Slab is just a way to reduce fragmentation inside the kernel memory allocation. You just take a page, you divide it in objects, and when you need an object, you just get it from the Slab. There are caches for common use object. Imagine inode. So you need a lot of inode on the system, so you need an inode object many times. You need to free and get it many times. And there are also slabs, caches, for generic purpose allocation. The equivalent of the malloc call on userland, it's the command alloc call inside the kernel land, or the command-alloc call on Linux. And the slab cache is called command alloc n. N stands for the number, so command alloc 32, command alloc 64, and so on and so forth. This image, which is taken from Solaris internals, if you want to read a good book on the Solaris kernel, take this one. This image summarizes the use of the slab. If you're somehow familiar with the Linux slab, you will see that there is one more point of interaction inside this image, and which is a little bit of a problem when you come up into exploiting slab overflow on Solaris. The main idea is that the allocation starts from the top, and it will check if in the cache that every CPU holds, there is some available objects. Those rectangles that you see are called magazines. Magazines are an array of pointers. Each one of those magazines keeps one pointer to an empty, which is a white one, or a full object, which is keeps an available object, which is like a blue one, or an empty slot, which is a white one. You can release an object inside an empty slot, or you can take an object from a full one, from a blue one. So what will happen is, we ask for an object, we check the CPU cache, the per CPU cache. This is done because if you have a time processor, you want to reduce locking as much as possible, so having a per processor CPU cache is good. And if you don't have anything there which is working, everything is full, everything is empty, you go back to the depot layer. The depot layer is only one for all the CPUs, and so contention is analyzed at this level, and it will provide you a full magazine of objects or an empty magazine of objects. At the end, there is the slab, which is the same as Linux, basically. And the slab is interesting because all these things you see are all in the same physical page. That means that all those buffers are one after the other. So what is not true inside magazines is true inside slab. You see the point? We want to get to the slab, and we want to have two buffers, one near the other, so we can free the first one, allocate our overflowing buffer, and go on the other one. That's basically what I told you. This is the sequence when I allocate, and the same sequence is performed when you release an object. So imagine the system starts, so nothing is allocated. You go back up to the slab layer, you allocate an object, then you free it. It will be freed at the first available point, and the first available point will be an empty magazine. So it will stay in the magazine. That's the reason why inside magazines you have pointer which belongs to different pages, and so you can't rely on them. This is what magazines are: containers of pointers. You have no guarantee, put that in mind because it's important, that two subsequent objects will be adjacent in memory. Magazine size is dynamically adjusted. This is a thing you don't really have to care much about. But if you're performing a long exploit, then you might take care about that. Because if another CPU is competing for getting magazines, then that will translate in contention at the depot layer, and the kernel thread will enlarge the size of magazines, changing the calculation we have been doing up to that point. The default scheduling time of this thread is 15 seconds. Whoever you ever run an exploit knows that on a local machine, 15 seconds is usually more than enough. What we need to do is control precisely the state of the slab allocator, so we can manage to exploit this kind of vulnerability. We use the user land. We get all the information from the user land. We use the kstat tool, kstat. The kstat provides statistics for basically every subsystem inside the kernel, and also to slabs. This is an example of the output of the kstat commands applied to the generic purpose cache command alloc 64. The one in blue are the one we are interested into. And take a quick look and remember them. which is not easy, I know. But anyway, what you need is buff available, which tell you how many objects are free. So we need to exhaust somehow the cache, so that once the cache is exhausted, it will behave just like the cache at the start of the system. It will be a predictable cache. If something is predictable, that means that it is exploitable. So we want something predictable. So we exhaust all the cache, and we check, thanks to Slab create, if a new slab has been created. At that point, we know that if we allocate some object from now on, they will be all one after the other in memory, all subsequent in memory. Full magazine, empty magazine, magazine size are very useful to check if your exploiting is going to the right direction. And so if it is, perform the overflow. If it is not, don't perform it, because it might happen that it will crash the machine. Thanks to that, we managed to write exploits which are almost one shot on the Solaris kernel. At that point, what we need is to exhaust all the possible objects which are there. And to do that, what you basically need is just some way to unlock a large number of objects. The solution is using the IPC services. You can use IPC get to unlock a wide large number of objects from inside the kernel, and so exhaust the slab. The only thing you need now is some object that you want to overflow into, some object with a pointer. We don't have enough time here to go on this one. Just wait 2 weeks and an exploit will be released and you will see it. What we talked before, we say that if you don't trash the stack, then it is easy. You can use the stack which is already there. But what happens if we trash the stack? What happens if a common overflow on the stack happens inside the kernel? Is that exploitable? It is. Because we can recreate the stack. The best way to understand how to recreate the stack is checking how it is used by the kernel. The first thing, this is exactly the starting code for the user tab, which is the tab which is called when you issue a system call. The first part just gets you windows available inside the kernel. You don't really care about that. What you really need to know is that there is a member inside one structure inside the kernel, which basically is used as the starting address point of the stack. So every operation on the stack will start from this address. So if we know how a system call will behave, we know how the stack will look like, at least at which distance everything will be. This is very good, because one more thing happens. There is a save. Save basically means that the new Windows is allocated, that the frame pointer will be placed equal to G6. G6 is our stack. The stack bias is just a constant. The value is offset by. On 64-bit kernel, it is 2047. On 32-bit kernels, you will never find a 32-bit kernel, so don't worry. But anyway, it's 0. So we know that this value can be an FP value, and so we can use it to at least have a good point to store register from. And this point is the way what we want to get back to the user land. What we need now is just the correct return address. I mean, we know where to get into the stack, but we don't know yet which function will return from that point on the stack. If we manage to find it, then we are done. Then our exploit is basically done. The good thing is that the L3 register, the local free register, which is saved on the stack upon a function call, which is the first one you see, actually they will be executed from the bottom to the up. But it's easier, in my opinion, to see it like that, so I put it like that. And the L3 register actually contains the address of the syscall trap for LP64, or the syscall trap 32 for LP32 syscall, depending on which kind of syscall you issue. If it's a 32-bit syscall, because you can have a 32-bit user land on a 64-bit kernel land, then it will be using syscall trap 32, otherwise it will be syscall trap. At this point, we know that somewhere on the stack, and you remember that we know the address of the stack, so we know where exactly, we know our return address. The only thing we don't, this is just to prove that I'm not telling you lies. You can check, this is the stack, the T-stack address, and you can see that the address of syscall trap 22 is exactly where we expect to find it, or that is exactly where the L3 register is saved. So we get to our shellcode. This shellcode it's a working shellcode for kernel exploitation of a stack overflow. As you see, we use the syscall tab32 address on the red line. We use the FP. You see the blue line is just using the FP from the keythread tstack member. The first part is the same we saw before, so we know that in G7 there is a keythread stat. Then we use tstat to get to syscall tab32. We offset to the stack bias constant, and then we jump in the exact point inside syscall tab32 because it was at some point syscall tab32 called the user trap, so we want to get at that point. Yes, these addresses are coded. So that's not wonderful. I mean, if you know the kernel which is running, so you do a unim -a on Solaris 9 and Solaris 10, this value is OK as long as you use it. But it might not be OK if a lot of people start using OpenSolaris and compiles this kernel. But what we can do is writing an approach scanning from syscall tab32 and calculate it at runtime. I won't show you this one here. It will be online after the talk, in a couple of weeks after the talk. You will see it's just like 5 instructions to do that. So a completely reliable kernel exploit, shellcode for the kernel stack vulnerability can be done in 10, 12 instructions, which is more than enough. With that, I leave the stage to sgrakkyu. This is done for the Solaris SPARC. We will talk to you about Windows race condition. I finished.
Hi, and first of all, I apologize for my bad English. I hope you enjoy anyway this part of the talk. In this part of the talk, we speak about race condition in Windows and then third-party software integrated in that. We are used to see user space race condition like in signal handler or in user space multiple thread, or time to check, time to use attack like symlink attack race condition. In kernel space, things are different because most of the kernel data is shared globally, because virtually any place in the kernels can be vulnerable by a race condition if the code don't use properly locking mechanism. We have different type of race condition between multiple process, between interrupt and process context, or between multiple process context accessing user space. We deal with the user space case on uniprocessor system because it's more difficult to exploit this type of vulnerability respect to symmetric multiprocessor system because there is one processor and one process at a time run on the computer. Some basic knowledge about scheduling and memory management to better comprehend the rest of the slide. The key concept is that we can exploit race condition if we making process switch, context process switch deterministic. We can make deterministic with respect to the time and to the place. Sometimes it's better to make the process switch working without the knowledge of where the process switch occurs, but only that it must occur. At the time, we must oblige the process to sleep at deterministic time, but also in a deterministic place. We see later. The process may sleep voluntarily, waiting for some resource, with demand paging. That is the most important key, as we see later. If the timer slice expires or during expected operation, for example, on Linux, it may sleep call. The most important thing is the demand paging because we use that feature of kernel to exploit race condition. Another key is that a process that runs with higher priority is killed before or in place of a lower priority process. Briefly about demand paging. Demand paging is used by the kernel to optimize disk caches because they not transfer all the data from disk to memory, but they wait for the process to make the first access to the memory, and only then it transfer only the used part of the program. Then in that moment the process is put to sleep because there is a disk access. This cache is important because we can the page fault when the kernel detects a page fault, the page fault handler don't transfer only the page we need, but transfer also other page nearer that we need and store them in a disk cache. It's important to know this because we must full the disk cache to empty our data from this cache, because a page fault that touches this cache instead of the disk don't put the process to sleep. Then there maybe that may put the process to sleep, but it's not deterministic. How we can force a process to sleep is a generic approach. I take either Linux or Windows. We can take a page clustering value if we need to force the sleep in a deterministic place with when the kernel read some address. If we need only to make a process switch without knowing exactly what address, the page clustering is not needed. We can take it with the API from proc, and there is the number of pages that the kernel maps in the user space when a page fault occurs. Then we must write into a file the data we must want into memory, and then map it into memory using shared mapping. With the map on Linux, so with create file mapping and mapping of file on Windows. We must then keep out our data from the cache, because if the data remains the cache, a page fault in memory don't put our process to sleep always. Then for this, if we have administrative right, we can do some thing to make this faster, as we see later, as we next. If you have not that, we must access file system, many files on the file system, like searching a huge file, or we can create or finding a already huge file, map it in memory, and try to keep all this data into memory. If we have not a huge amount of RAM in our machine, we can in a deterministic way put our data away from cache. And then if a new access to it makes a deterministic fault, and then a switch. This is an example of a payload in memory. In this case, we use this payload in exploit for MD64 kernel on Linux. In this case, we need also that the fault happens exactly at the precise address. Then we have to align the address of the second structure in the clustering value, as you see before. In this example, the kernel, when the kernel accesses the first structure, nothing happens. When access exactly the first control message len of the control message structure in the second structure here, a page fault occurs, and another thread waiting for the race can change the first len, making a len miscalculation and the buffer overflow in the kernel. This is the real topic. How third-party software integrating Windows, like desktop protection or personal firewall or antivirus, are implemented inside Windows, inside the Windows kernel, and how we can exploit this race condition in the system to bypass control on that. There is some work about this topic in some Unix framework IDS and OpenBSD, and so I want to analyze this because in Windows there is no such research in depth, and seems that those product will continue to use API kernel space hooking at last on Windows XP for a long time. This is brief history of how this product manage to protect Windows system. All the user space API hooking, this is not more used. Kernel device filter, this is used to monitor device or file system, and this is placed in a lower deep in the kernel and don't manage with the user space, this is quite safe. And the API kernel space hooking that is used by most of these products seem to be secure respect to the API user space hooking, but is a broken design because it's placed in the middle of the chain of the API hooking, because and so here either API wrapper then original API access user space. How they are implemented? They are implemented as an API wrapper. They are called before the real API. There is some check before, and some products make a check also after the call of the original API. Where the hook is placed, mainly is placed in a service, the system service description table, or patching the initial bytes of the API, like some malware. Here a simple example how API hooking on SSDT is done. The problem is that the first API the wrapper API of the personal firewall access the user space, and then also the original Windows API access the same user space in a different moment. This is a typical time to check, time to use fault inside the kernel. And finally it return in the routine that come back to user space. There is some programming error in SSDI hooking. The first are implementation error of individual antivirus. The third and the fourth are the logical error, design error that are quite founded in all this product. Mainly the first is a design error of the entire implementation of this type of check. I mainly discussed the last two. I managed to show two types of this vulnerability using the first three functions that are monitored by all these products, and that are write virtual memory, that is used to write memory inside another proxy address space, create thread and set value key as an example for double user space access vulnerability. In the first example, by virtual memory, many products don't manage to control every access to the process, but try to get only dangerous environment, like in this function, monitoring only that there is no write inside another process access space if the process access space memory we try to write to is executable. In this case, stop or deny the operation. We can bypass it using more API that change the environment that is checked by the personal firewall. For example, creating a read-write memory chunk, then writing with write virtual memory that is not denied because it's not executable, and then modify another time the memory using page execute protection using protected virtual memory. This is only an example of multiple API, but there is other example I can make. More interesting is the design error of the double user space access. I take the set value key function, but it's the same for the create thread. This function is used to write a value inside a key, a already open key in the registry. How personal firewalls or antivirus works in this case? Normally they allow the open of key, and then deny every write inside it. Then first get the key handle, a handle descriptor, find the object referring to this handle, then work, match some of the environment we pass through the API with the key, and deny or allow based on that value. We can bypass it using find two main techniques based on API prototype, based on what argument we can pass to the API. And the first invite parameters race. There are different prerequisites. In In this sample, the API must have at last one external structure to access, like Unicode struct. The API must deference user space memory at last once, and the API wrapper must pass invalid environment to the real API. Then the antivirus may be fooled by invalid structure. What you can make is to map a user space, a file to user space memory, try to empty this memory from this cache, constructing invalid structure, and create a second thread waiting for the race, and that when the race kick up, he'll change the structure in a suitable manner. Then we can see a graph to know better how it works. Here's a user space stack pointing to a user space structure. As you see, the first structure is invalid, and many antivirus implementations don't manage this type of structure. When the arguments are copied in the kernel stack, we have first the API wrapper of the antivirus copy the argument inside the structure. Then when he tries to access user space in a second argument, a purge fault occurs because the data is not in the memory but on the disk. And another thread wake up had been scheduled and change in the right manner the structure. When the antivirus don't manage the structure that already copy inside his stack memory, pass all the arguments to the original API that find a new structure that is valid and can manage. The other telling is more reliable and can be used with all functions that had at last an handle, that most of the function in Windows. The API must deference also in that example at last once the user space to trigger the race. Also in this example we can we create file mapping on Windows. The user space memory, we must allocate an handle pointing to a safe object. As a safe object I intend an object that are not critical for the antivirus monitoring it. For example, we can open a registry key that is not monitoring, that is not a critical key. We try to empty the memory from this cache to getting the race. Create a second thread waiting for the race that this time don't recreate a structure, but simply close the handle that we have passed and reopen it using a different controller object. Now the object we want to write to really. Here's the graph, and this is more clearly all the work. This is the three arguments, the handle in yellow, and the other two are pointer to user space data, the Unicode struct and the address. Now all the struct is okay, then there is no invalid value inside them. When they are copied to the kernel start getting handle and resolving the handle with the object. We see the handle is an index inside, like an index inside a kernel handle table that point to the real object. Then the wrapping routine of the antivirus get that pointer to the real object using the handle. Then when try to access a second parameters in the user space, for example here in data, a race occurs because a page fault occurs, a new thread can be scheduled, and the new thread, what do the new thread? The new thread simply close the handle and then reopen it using another object. Now, because the kernel handle table is shared among threads of a unique process, the same handle in the same handle that is copied before in the kernel stack point to a new object. Now, when the antivirus wrapper pass arguments to the original API find the same index pointing to a different object, what we can write to. For example, run once or other key monitored by antivirus. Some tips against this type of vulnerability. There is no really workaround. All workaround, or quite all workaround, can be bypassed. Mainly in the second technique, because all wrapper functions that resolve the object and then use it are vulnerable to this type of arrays. I don't test for all products that make personal firewall antivirus in Windows, but what I test are vulnerable. There is some difference in exploitation vector, because in the first case, because no all antivirus threat invalid instruction in the same manner. In the second case, instead, is always the same payload, works quite well. There is some tips, for example, when you can empty faster the cache, for example, when we have a huge memory, more than 1 or 2 gigabytes, in a desktop is now quite common. If you have admin right or at last quota privilege, and some other privilege we need is to enlarge the process working set size, then using virtual lock and map file X to map a huge anonymous mapping and block all memory inside it. Then virtual lock all the virtual memory inside physical memory. Then the physical memory was full, and the rest of the access to the memory force a swap off of the cache. If you have not admin rights, this is the opposite technique that we can make smaller, like also until 0, the process working set. Then when we try to fill the cache, the process is our data in the process is the first to be putting out of the cache. But we always try to fill the disk cache if we have not admin rights. How to fill the antivirus when the race doesn't kick up? Because race condition is with this technique can be deterministic, but sometimes can happen that he doesn't kick up. We can, when preferred, use the second technique, the handle object redirect attack, because it's safe in the point of view of the antivirus logging. Because if the race doesn't kick up, the antivirus get the old object we pass, then not critical object, and there is no log or pop-up from the antivirus. The nasty thing can happen is that the exploit don't work, then we can write to the handle we intended to, but we can remake another try without getting discovered by the protection system. There is a reference, then the article we wrote with tweets about kernel exploiting. This part is not inside that because it was not completed the date where the article will come out. And here related to this part is a very good article about some Unix IDS exploiting using a similar technique, either in uniprocessor and simple symmetric multiprocessor system. Then I finished. There is any questions for me?